This film takes you on a journey through space and time. I want to tell you the story of an instrument that has vastly improved our view of the skies, sharpening our perception of the universe and penetrating ever deeper toward the furthest edges of time and space. Looking at the night sky, we see the familiar twinkle of starlight, light that has traveled enormous distances to reach us. But we're not seeing the stars themselves flicker.
The universe is gloriously transparent. The light from distant stars and galaxies can travel unchanged across space for thousands, millions, even billions of years. But then, in the last few microseconds before that light reaches our eyes, the accurate view of those stars and galaxies is snatched away. This is because, as light passes through our atmosphere, the ever-changing blankets of air, water vapor, and dust blur the fine cosmic details.
So for many years, astronomers around the world longed for an observatory in space. As early as 1923, the famed German rocket scientist Hermann Oberth suggested a space-based telescope. However, it would be decades before technology caught up with the dream. The American astronomer Lyman Spitzer came up with a more realistic plan for a space telescope in 1946.
From a position in space above Earth's atmosphere, a telescope would be able to detect the pristine light from stars, galaxies, and other objects well before it was distorted by the air we breathe. The result? Much sharper images than even the largest telescopes on the ground can achieve. Images limited in sharpness only by the quality of the optics. In the 1970s, NASA, the National Aeronautics and Space Administration, and ESA, the European Space Agency, began working together to design and build what would become the Hubble Space Telescope. The name is a tribute to Edwin Powell Hubble, the founder of modern cosmology, who in the 1920s proved that not all that we see in the sky lies within the Milky Way. Instead, the cosmos extends far, far beyond. Hubble's work changed our perception of mankind's place in the universe forever, and the choice of naming the most magnificent telescope of all time after Edwin Hubble could not have been more appropriate. It took 2 decades of dedicated collaboration between scientists, engineers, and contractors from many countries before Hubble was finally finished. On April the 24th, 1990, 5 astronauts aboard the Space Shuttle Discovery left on a journey that changed our vision of the universe forever. They deployed the eagerly anticipated space telescope in an orbit roughly 600 kilometers above the Earth's surface. On Earth, the astronomers waited impatiently for the first results. But less than 2 months later, it was clear that Hubble's vision was anything but sharp. The mirror had a serious flaw.
A defect in the shape of the mirror prevented Hubble from taking sharp images. The mirror's edge was too flat, by only a mere 50th of the width of a human hair. But to accomplish its mission, Hubble had to be perfect in every tiny detail. The disappointment was almost too great to bear. Not only amongst astronomers, but also for American and European taxpayers. Nevertheless, over the following 2 years, scientists and engineers from NASA and ESA worked together to design and build a corrective optics package named COSTAR, for Corrective Optics Space Telescope Axial Replacement. Hubble's masters now faced another tough decision. Which science instrument should they remove so that COSTAR could be fitted to Hubble? They eventually chose the high-speed photometer.
Hubble's first servicing mission in 1993 has gone down in history as one of the highlights of human spaceflight. It captured the attention of both astronomers and the public at large to a degree that no space shuttle mission since has achieved. Meticulously planned and brilliantly executed, the mission succeeded on all counts. COSTAR corrected Hubble's eyesight more perfectly than anyone had dared to hope.
When the first images after the servicing came up on the computer screens, it was instantly clear that the glasses taken up by the astronauts were completely correcting Hubble's nearsightedness. Hubble was finally in business.
That was only the first time the space shuttle visited Hubble. The telescope was designed to be upgraded to keep utilizing new capabilities. When more advanced instruments, electrical or mechanical components became available, they could be installed. Plus, just as your car needs servicing, so Hubble needs tuning up from time to time. Engineers and scientists periodically send the shuttle to Hubble so that astronauts can upgrade it using wrenches, screwdrivers and power tools, just as your mechanic does with a car. There have been 4 servicing missions so far, in 1993, 97, 99 and 2002, all undertaken by astronauts transported into space by NASA's Space Shuttle. The next one was supposed to occur in 2005, but was unfortunately cancelled in the aftermath of the tragic Columbia crash.
Hubble's future is uncertain. It was originally designed to operate for 15 years, but it's now expected that its life could be extended to 20 years. Hubble is still producing the most astonishing results astronomers have ever known.
Hubble's important mission will eventually come to an end. An unmanned probe will link up with Hubble in orbit and dock with it. When leaving Hubble, the robot will leave behind a rocket module so that after some more years of fruitful observing, engineers on the ground can activate these rockets to control Hubble's final descent into the atmosphere and to a peaceful final resting place in the ocean. However, the retirement of the Hubble Space Telescope will not signal the end of our unrivaled view of the universe. Rather, it will mark a new beginning, an era of even more amazing discoveries and images from space. For Hubble has a successor. The James Webb Space Telescope is being designed right now and may be launched as early as 2011. When that day comes, Scientists using the James Webb Space Telescope hope to discover and understand even more about our fascinating universe. Hubble is an upgradable space-based telescope orbiting at almost 600 kilometers, placing it well above most of our image-distorting atmosphere. It takes about 97 minutes to complete each orbit. It is designed to take high-resolution images and accurate spectra by concentrating starlight to form sharper images than are possible from the ground, where the atmospheric twinkling of the stars limits the clarity.
To gather as much light as possible from the faint objects it observes, any telescope needs the largest mirror it can get. Despite Hubble's relatively modest mirror diameter of 2.4 meters, it's well able to compete with ground-based telescopes having mirrors that are 10 or 20 times larger in collecting area. Hubble is a large satellite, about 16 meters long, or the size of a small bus. It's also one of the most complicated pieces of technology ever built. It contains over 3,000 sensors that continuously monitor the status of the hardware, so that technicians on the ground can keep an eye on what's happening. Time on Hubble is a precious commodity. Astronomers around the world regularly ask for much more time than is available. Keeping Hubble operating 24/7 is no small task. Not a second must be lost, and all operations, from observing to the so-called housekeeping tasks, such as repositioning the telescope or uploading new observing schedules, are meticulously planned. For astronomers, the most important components of Hubble are its scientific instruments. There are two groups of instruments in Hubble, here and here. The different instruments serve different purposes. Some are for making images. Some are designed to dissect the light from the stars and galaxies by spreading it out to form a rainbow-like spectrum. Hubble's unique vantage point in space makes it capable of observing the infrared and ultraviolet light that is otherwise filtered away by the atmosphere before it can reach telescopes on the ground. These forms of light reveal properties of celestial objects that are otherwise hidden from us. Some instruments, like ACS, the Advanced Camera for Surveys, are better for visible and ultraviolet observations. Some, like NICMOS, the Near-Infrared Camera and Multi-Object Spectrograph, are best for infrared observations.
Different mechanical and electrical components keep Hubble functioning. The power for Hubble comes from solar panels on the side which convert sunlight into electricity. Gyroscopes, star trackers and reaction wheels keep Hubble steady and pointing in the right direction, not too close to the Sun, Moon or Earth, as they would destroy the light-sensitive instruments, and accurately towards the objects being studied for hours or days at a time. Hubble has several communication antennae on its side that are necessary for sending observations and other data down to Earth. Hubble sends its data first to a satellite in the Tracking and Data Relay satellite system, which then downlinks the signal to White Sands, New Mexico. The observations are sent from NASA in the United States to Europe, where they are stored in a huge data archive in Munich. No single nation could undertake such an enormous project. Hubble has been a major collaboration between NASA and ESA, the European Space Agency, from an early stage in its life. Hubble has been of paramount importance to European astronomy. European astronomers regularly win more than 15% of the observing time with Hubble, resulting in several thousand scientific publications over the years. 2 groups of European specialists work with Hubble. There are 15 people from ESA currently working at the Space Telescope Science Institute in the USA, and 20 others make up the Space Telescope European Coordinating Facility in Munich, Germany. There are no boundaries in space. In this vast universe, our closest relatives are the objects within the solar system. We share the same origin and the same destiny.
Our solar system was formed about 4.5 billion years ago from a huge gas cloud. Ironically, it could have been the deadly force of a thermonuclear blast from an exploding star in the vicinity that triggered our creation.
The devastating force of the blast may have disturbed the precarious equilibrium of the original gas cloud, causing some of the matter to collapse inwards towards the center, creating a new star, our Sun, and a minute percentage of the collapsing matter became the multifaceted assembly of planets that we have around us today. We are, in other words, just the leftovers of our Sun's birth. The planets were born in the rotating disk of dust and gas left behind as our mother's star was formed. The rocky planets formed in the inner solar system, while the enigmatic gas giants were formed farther out. And then, when a fierce wind of smashed atoms began to blow from the Sun, or perhaps from hot nearby stars or a nearby supernova, only sizable planets could maintain their gaseous surroundings, and the last wisps of the tenuous cloud between the planets was whipped away. So in our solar system's zoo of celestial bodies, there are rocky worlds and giant gaseous planets.
Even now, there's no exact estimate of the amount of matter, or even the number of planets that exist in the solar system. Since Pluto's discovery in the 1930s and its satellite Charons in the 1970s, astronomers have been trying to figure out if there's anything else out there beyond the 9th planet. In 2003, Hubble spotted something moving fast enough across the background of faraway stars to be an object within the solar system. Estimates show that it could be about the size of a planet, and it's been named Sedna, after an Inuit goddess. Sedna may be 1,500 kilometers in diameter. That's about 3/4 the size of Pluto, but so far away that it appears just as a small cluster of pixels, even to Hubble. Nevertheless, it's the largest object discovered in the solar system since Pluto.
The Sun is about 15 billion kilometers from Sedna, 100 times further than Earth's distance from the Sun, and barely gives out as much light and heat as the full moon. So Sedna is engulfed in an eternal bleak winter.
Sedna is not the only mysterious object out there. Debris from the formation of the planets is still floating everywhere in the form of asteroids and comets of various shapes and sizes. Sometimes their orbits can lead them on catastrophic courses.
The Hubble Space Telescope witnessed the final journey of the comet Shoemaker-Levy 9. It was torn into numerous pieces by Jupiter's gravitational pull when it passed the massive planet in the summer of 1992. 2 years later, these fragments returned and drove straight into the heart of Jupiter's atmosphere. Hubble followed the comet fragments on their last journey and delivered stunning high-resolution images of the impact scars. Our Earth could easily fit into any of these black bruises. Space probes with sophisticated instruments are frequently sent to the planets of our solar system. They provide close-up investigations of these distant places. Hubble too provides its own unique service by opening a window on our solar system that is never closed. We've gained unprecedented views of storms on other planets, their changing seasons. And unprecedented views of other atmospheric events, such as aurorae, known on Earth as the Northern and Southern Lights. Even though the solar system clearly has many more surprises in store for us, Hubble has also turned its eye out towards other stars looking for planetary systems. Astronomers are beginning their search for life elsewhere in the universe. To start with, they are concentrating on finding Earth-like planets. In 2001, Hubble made the first direct detection of the atmosphere of an extrasolar planet and partially determined its composition. Measuring the chemical makeup of extrasolar planetary atmospheres will one day allow us to search for the markers of life beyond Earth. All living things breathe, and this changes the composition of the atmosphere in readily detectable ways. Astronomers believe there are many planetary systems similar to ours, orbiting other stars throughout the galaxy. The birth, life, death, and rebirth of stars continues in an unending cycle, in which stars born of gas and dust will shine for millions or billions of years, die and return as gas and dust to form new stars. The byproducts of this continual process include planets and the chemical elements that make life possible. So throughout the entire vastness of space, the eternal ebb and flow of life continues. Our Sun, that vital source of energy for life on Earth, is a star, a totally unexceptional star, just like billions of others that we can find throughout the galaxy.
A star is nothing but a sphere of glowing gas. It forms out of a compressed cloud of gas and releases energy steadily throughout its life because a continual chain of nuclear reactions takes place in its core. Most stars combine hydrogen atoms to form helium through the process called nuclear fusion, the same process that powers a devastating hydrogen bomb. In fact, stars are nuclear factories that convert lighter elements into heavier elements in a series of fusion reactions. They will keep glowing until they run out of fuel. And that's it, a star's life, a quiet beginning and a steady progress to a sometimes violent end. But how can we be certain of this picture when an individual star like the Sun outlives humans by a factor of a few 100 million?
To investigate the life cycle of a particular organism on Earth, we don't have to track an individual specimen's entire life. Instead, we can observe many of the organisms at once. This will show us all the different phases of its life cycle. For example, each stage of a person's life is a snapshot of the human experience. And so it is with stars.
Stars live and die over millions or even billions of years. Even the most reckless stars live for at least 1 million years, longer than the entire history of humankind. And that's why it's extremely difficult to track age-related changes in individual stars. To learn more about them, we must study different stars at every stage of life, and so piece together the entire cycle from birth to death. Hubble's vivid images have documented the tumultuous birth of stars and delivered many astonishing images in colourful detail.
The birth of stars in neighbouring stellar maternity wards can be used as a time machine to replay the events that created our solar system. Hubble has often had to work hard for this information, because these important clues about our genesis lie hidden behind the veil of gently glowing, dust-laden molecular clouds where stars are formed. There are stars forming everywhere in the universe. Enormous glowing pillars of dusty hydrogen gas stand sentinel over their cradles, basking in the light of nearby newly formed stars.
Hubble's ability to observe infrared light enables it to penetrate the dust and gas and reveal the newly born stars as never before. One of the most exciting of Hubble's many discoveries was the observation of dust disks surrounding some newborn stars buried deep inside the Orion Nebula. Here we are actually seeing the creation of new solar systems where planets will eventually form, just as they did in our own solar system 4.5 billion years ago. In the first stages of their lives, stars can stock up on gas from their original birth cloud. Material falling onto the star creates bubbles, or even jets, as it's heated and blasted out along a path that follows the star's rotation axis, a bit like the axis through a wheel.
Often, many stars are born from the same cloud of gas and dust. Some may stay together through their whole lifetime, keeping step as they evolve, like childhood friends that you keep for life. The stars in a cluster will all have the same age, but will have a range of different masses, and this means that very different destinies await them. Human existence is the mere blink of an eye compared with the life of a star. So the direct observation of a transition between different stages of a star's life can only come about by lucky chance. In 15 highly productive years, Hubble has allowed us to observe some stars aging in real time. The telescope has produced startling movies that allow us to witness how some of them do modify their appearance over this minute span of astronomical time. The stars containing the most mass end their lives cataclysmically, destroying themselves in titanic stellar explosions known as supernovae. For a few glorious months, each becomes one of the brightest objects in the entire universe, outshining all the other stars in its parent galaxy. Since its launch in 1990, Hubble has watched the drama unfold in supernova 1987A, the nearest exploding star in modern times. The telescope has been monitoring a ring of gas surrounding the supernova blast. Hubble has observed the appearance of bright spots along the ring, like gemstones on a necklace. These cosmic pearls are now being lit by supersonic shocks unleashed during the explosion of the star.
The ruins of an exploding star can hide a powerful engine. Hubble has probed the mysterious heart of the Crab Nebula, the tattered remains of an exploding star, vividly described by Chinese astronomers in 1054, and has revealed its dynamic center. The innermost region of this nebula harbors a special type of star, a pulsar. Like a beacon, this star rotates, emitting energy and light in a beam, and it powers the vast nebula of dust and gas surrounding it. However, not all stars end their lives so violently. Sun-like stars cool down once they run out of hydrogen. The center collapses in on itself and the heavier elements are burnt, causing the outer layers to expand and leak slowly into space. At this stage in a star's life, it's called a red giant. Our Sun will become a red giant in a few billion years. At that time, it will expand so much that it will swallow Mercury, Venus, and our planet too. But these stars are not finished quite yet. They can still become something quite extraordinary.
Just before they breathe their last breath, stars like our Sun go out in a final blaze of glory. In its final stages of nuclear fusion, stellar winds blow from the star, causing the red giant to swell to an enormous size. At the heart of this expansion, the exposed heart of the star floods the gaseous envelope with powerful ultraviolet light, making it glow. Because to early telescopic astronomers these amazing constructions looked a bit like the newly discovered planet Uranus, they became known as planetary nebulae. Hubble's keen perception shows that planetary nebulae are like butterflies. No two are alike. Hubble's dazzling collection of planetary nebulae shows surprisingly intricate glowing patterns. Pinwheels, swirling jets, elegant goblet shapes, barrel shapes, or even rocket engine exhausts. From its unique position high above the distorting atmosphere, Hubble is the only telescope that can observe the swollen outer envelope of these dying stars in full detail. Here we flip back and forth between Hubble images from 1994 and 2002. One of the greatest mysteries in modern astrophysics is how a simple spherical gas ball such as our Sun can give rise to these intricate structures. For some planetary nebulae, it is as if a cosmic garden sprinkler created the jets that stream out in opposite directions. Or could these amazing patterns possibly be sculpted by the magnetic field of a companion star that funnels the emitted gas into a jet? Whatever their cause, in only 10,000 years, these fleeting cosmic flowers disperse in space. Just as real flowers fertilize their surroundings as they decompose, the chemical elements produced inside the star during its life are dispersed by the planetary nebula to nourish the space around it, providing the raw material for new generations of stars, planets, and possibly even life. Because they disappear so quickly on a cosmic timescale, there are never more than about 15,000 planetary nebulae at any one time in our Milky Way. A more lasting monument to the dead star is the tiny heart it leaves behind. Known as a white dwarf, each of these exceptionally dense Earth-sized stars are fated to spend the rest of eternity gradually leaking their residual heat into space, until eventually, in many billions of years, they approach the frigid minus 270 degrees centigrade of space.
We live inside a huge star system, or galaxy, known as the Milky Way. Seen from the outside, the Milky Way is a gigantic spiral consisting of a central hub embraced by long arms. The whole system slowly rotates. Between the stars, there are vast amounts of dust and gas that we can see, and some unknown material called dark matter that remains invisible to us. Far from the center, out in one of the spiral arms, the suburbs of the Milky Way, there's a tiny star system, our home, the solar system.
When we look up on a clear night, we can see about 5,000 of the closest stars. Our eyes struggle to see beyond 1,000 light years because of the dust that blankets space and dims the distant starlight. So without a telescope, we can only see a minute portion of the entire 100,000 light-year wide Milky Way. For the Milky Way contains several hundred billion stars, many like our own Sun, although several 100,000 million is an almost unfathomable number. It is only the beginning. Astronomers believe there are more than 100 billion galaxies in the universe. How many stars would that be?
In a handful of sand, there can easily be 50,000 individual grains. Our Milky Way contains so many stars there can scarcely be enough grains of sand on a whole beach. There are so many galaxies containing so many stars in the universe that we would have to count every grain of sand on every beach on the whole Earth in order even to come close to the right number, and then there would be more stars in the universe. Let's take this grain of sand, 1 millimeter across, and place it here to represent the Sun. If we were to start walking towards the nearest star, it would take us the best part of a day to get there. We'd have to travel something like 30 kilometers.
So galaxies are mostly large collections of emptiness. If we could squeeze together all the stars in the Milky Way, they would easily fit into the volume of space between our Sun and the nearest star. In fact, to completely fill that volume, we would have to pack in all the stars from all the galaxies in the entire universe. When looking at the night sky, the universe seems motionless. This is because our lifespans are nothing but brief drops in the universal ocean of time. In fact, the universe is in constant motion, but we would need to watch for vastly longer than a lifetime to perceive that motion in the night sky. Given enough time, we would see stars and galaxies move. Stars orbit the center of the Milky Way, and galaxies are pulled together by each other's gravity. Sometimes they even collide. Hubble has observed numerous galaxies crashing together. Like majestic ships in the grandest night, galaxies can slip ever closer until their mutual gravitational interaction begins to mold them into intricate figures that are finally and irreversibly woven together. It is an immense cosmic dance, choreographed by gravity. When two galaxies collide, it's not like a car crash or two billiard balls hitting each other. It is more like interlocking your fingers. Most of the stars in the galaxy will pass unharmed through the collision. At worst, gravity will fling them out along with dust and gas to create long streamers that stretch 100,000 light years or more. The two galaxies, trapped in their deadly gravitational embrace, will continue to orbit each other, ripping out more gas and stars to add to the tails. Eventually, hundreds of millions of years from now, the two galaxies will settle into a single combined galaxy. It is believed that many present-day galaxies, including the Milky Way, were assembled from such a coalescence of smaller galaxies occurring over billions of years. Triggered by the colossal and violent interaction between the galaxies, stars form from large clouds of gas in firework bursts, creating brilliant blue star clusters. Our own Milky Way is on a collision course with the nearest large galaxy, the Andromeda Galaxy. They are approaching each other at almost 500,000 kilometers per hour, and in 3 billion years will collide head-on. The direct collision will lead to a magnificent merger between the two galaxies, during which the Milky Way will no longer be the spiral galaxy we are familiar with. Instead, it will evolve into a huge elliptical galaxy containing all of its own stars and all of those of the Andromeda Galaxy too. Seen from the Earth, the collision will look something like this. Although this will not happen for a very long time, there are other dark forces of nature in play everywhere around us, even as we speak. Black holes are the enigmatic villains of the universe, swallowing all that comes their way, allowing nothing to escape. So for astronomers, the center of a black hole is the ultimate unknown. No information can escape from within a black hole's gravitational stronghold. There is no way to find out what is in there. Not even light can escape. So how do we know that they are even there?
Black holes themselves cannot be observed directly. However, astronomers can see the indirect effect of black holes because the one thing they do possess in abundance is gravity. Hubble's high resolution has revealed the dramatic distorting effects of black holes on their surroundings. And not just gravity. Astronomers find that when material is packed tightly enough around a black hole, it can ring like a bell. This is the actual note produced by a black hole some 250 million light-years from Earth. It reverberates through the disk and has been altered here to fall within the range of human hearing. In reality, it's B-flat, some 57 octaves below middle C. Astronomers believe that black holes are singularities, simple points in space. No volume, no extension, but infinitely dense. Black holes can be created during the final collapse of a massive star many times the size of the Sun. The stellar corpse left after the demise and collapse of a massive star can be so heavy that no force in nature can prevent it crumpling under its own weight into an infinitely small volume. Although matter has apparently disappeared, having been compacted into nothingness, it still exerts a powerful gravitational pull, and any stars or other objects that come too close can be pulled in.
For any black hole, there is a point of no return called the event horizon. Once something, a nearby star, say, is pulled in past this point, it will never be seen again. On its way towards the event horizon, the doomed star will begin to follow a fatal spiraling orbit. As the star approaches the black hole still further, the matter closest to the hole feels a greater attraction than the rest of the star, sucking and stretching the star out towards the hole, until the immense tidal forces pull it to pieces and devour it. Quirkier aspects to these objects too. A twisting of space and time that warps and slows even the passage of time. All objects with a mass deform the very fabric of space and time, but black holes do this to an extreme degree. According to Einstein's famous theory of general relativity, an intrepid traveler who could visit a black hole and hang above the event horizon without being swallowed would eventually return to find himself younger than the people he had left behind. Perhaps the most curious objects astronomers have hypothesized about are wormholes. A wormhole is essentially a short cut through space-time from one point in the universe to another point in the universe. Maybe wormholes, if they exist, will someday allow travel between regions in space faster than it would take light to make the journey through normal space.
Hubble has shown that black holes are most likely to be present at the centre of all galaxies. There's one at the centre of our Milky Way, a giant, supermassive black hole, perhaps 1 million times bigger than those produced by the collapse of a single massive star. It could be the result of a merger of many stellar-sized black holes formed during the remote history of our galaxy.
When two galaxies collide, the black holes at each of their centres will perform an elaborate dance. Long after the two galaxies have merged into one, their central black holes continue to orbit each other for hundreds of millions of years before their final violent merger into a single weighty black hole. This final process is so powerful that it changes the fabric of space-time enough that we may be able to observe it from the Earth with a new breed of gravitational wave telescopes or from special spacecraft in orbit. However, compared with the millions of years it takes for galaxies to merge, the final cataclysm at the cores would be relatively brief. So the odds of seeing such an event are small.
Until as recently as 50 years ago, astronomers thought the universe was a mostly peaceful place, but this is far from the truth. Space is often shaken by violent events. Cataclysmic explosions of supernovae, collisions of whole galaxies, and the tremendous outpourings of energy resulting from matter crashing into black holes. It was the discovery of quasars that gave us the first glimpse of this turmoil. To ground-based telescopes, quasars look like normal stars, and that's exactly what astronomers first thought they were, naming them quasi-stellar objects. But quasars are in fact much brighter and further away than stars. They can shine more brightly than 1,000 normal galaxies and are powered by supermassive black holes.
Stars that orbit too close are pulled apart, draining into the quasar-like water into an enormous cosmic sink. The spiraling gas forms a thick disk heated to a high temperature by its free-fall motion towards the black hole. The gas blasts its energy into space above and below the disk in colossal jets.
Quasars are found in a wide range of galaxies, many of which are violently colliding. There may be a variety of mechanisms for igniting quasars. Collisions between pairs of galaxies could trigger the birth of quasars, But Hubble has shown that even apparently normal, undisturbed galaxies harbour quasars. But quasars are not the only high-energy objects astronomers have found. A serendipitous discovery is something you make whilst looking for something else. Such events have often changed the course of astronomy. Gamma-ray bursts were discovered serendipitously in the late 1960s by US military satellites on the lookout for Soviet nuclear tests. Instead of finding the most devastating detonations produced by humans, some of the most powerful blasts in the entire universe were spotted.
These astoundingly energetic blasts of gamma rays are detected at least once per day from random directions in the sky. Although gamma ray bursts last only a few seconds, the energy they release is equal to the amount of energy radiated by our whole Milky Way over a couple of centuries. Gamma rays are not visible to the human eye, and special instrumentation is needed to detect them. For 30 years, no one knew what caused these bursts. It was like seeing the gamma ray bullet fly by Earth without ever glimpsing the weapon that fired it. Together with nearly all other telescopes in the world, Hubble looked for the smoking gun for many years. It observed the positions in the sky where gamma-ray explosions had been seen, trying to find any object at that location. But all efforts were in vain, until... In 1999, Hubble observations were fundamental in determining that these monstrous outbursts take place in far distant galaxies. The cause could be the blast produced in the final cataclysmic collapse of a massive star, or the dramatic encounter of two very dense objects such as two black holes, or a black hole and a neutron star. Black holes are certainly some of the most exotic objects in the universe. As well as affecting matter, they can also show up in some other spectacular ways, because their enormous gravitational fields can also deflect light. In fact, rays of light that pass close to a black hole will not follow straight lines, but will be bent into new paths, creating a natural telescope that can peer further into space than ever thought possible. Just as a wanderer in the desert sees a mirage when light from remote objects is bent by the warm air hovering just above the sand, we may also see mirages in the universe. The mirages we see with a modern telescope such as the Hubble Space Telescope do not arise from warm air, but instead from remote clusters of galaxies, huge concentrations of matter.
Long ago, some people thought the Earth was flat. This is not surprising, since in our everyday lives, we're not aware of the curvature of our planet. Space is actually curved, although we can't see that for ourselves on a starry night. The curvature of space does, however, produce phenomena that astronomers can see.
One of Albert Einstein's predictions is that gravity warps space and therefore distorts rays of light in the same way that ripples on a pond create a warped honeycomb pattern of light on the sandy bottom. Light from distant galaxies is distorted and magnified by the gravitational field of massive galaxy clusters on its path to Earth. The effect is like looking through a giant magnifying glass, and the result is called gravitational lensing.
The weird patterns that rays of light create when they encounter a weighty object depend on the nature of the lensing body. Thus, the background object can appear in several guises. Einstein rings, where the whole image is boosted and squeezed in a circle of light. Multiple images, ghostly clones of the original distant galaxies. Or distorted into banana-like arcs and arclets. Though Einstein realized in 1915 that this effect would happen in space, he thought it could never be observed from the Earth. However, in 1919, his calculations were indeed proved to be correct. During a solar eclipse expedition to Principe Island near the west coast of Africa, led by the renowned British astronomer Arthur Eddington, the positions of stars near the obscured solar disk were observed. It was found that the stars had moved a small but measurable distance outwards on the sky compared with when the Sun was not in the vicinity.
Nowadays, faint gravitational images of objects in the distant universe are observed with the best telescopes on Earth and, of course, with the sharp-sighted Hubble. Hubble was the first telescope to resolve details within the multiple arcs, revealing the form and internal structure of the lensed background objects directly. In 2003, astronomers deduced that a mysterious arc of light on one of Hubble's images was the biggest, brightest, and hottest star-forming region ever seen in space.
It takes fairly massive objects, for example clusters of galaxies, to make space curve so much that the effect becomes visible in deep images of the distant universe, even with Hubble's astonishing resolution. And so far, gravitational lenses have been observed mainly around clusters of galaxies, which are collections of hundreds or thousands of galaxies and are thought to be the largest gravitationally bound structures in the universe.
Astronomers know that the matter we see in the universe is just a tiny percentage of the total mass that must be there. For matter exerts a gravitational force, and the visible stuff is simply not enough to hold galaxies and clusters of galaxies together. Since the amount of warping of the banana-shaped images depends on the total mass of the lens, gravitational lensing can be used to weigh clusters and to understand the distribution of the hidden dark matter.
On clear images from Hubble, one can usually associate the different arcs coming from the same background galaxy by eye. This process allows astronomers to study the details of galaxies in the young universe and too far away to be seen normally with the present technology and telescopes.
A gravitational lens can even act as a kind of natural telescope. In 2004, Hubble was able to detect the most distant galaxy in the known universe, using the magnification from just such a gravitational lens in space.
Light may travel through a vacuum at the highest speed anything can ever reach, but it's still a finite speed. This means that it takes a while for light rays to travel between 2 points in space. The speed of light in space is about 300,000 kilometers per second. Now 300,000 kilometers is nearly the distance from the Earth to the Moon, and so it takes just over a second for light to travel from the Moon to the Earth. So when we look at the Moon, we're seeing it as it was just over a second ago.
Who hasn't thought about what it would be like to travel in time? The finite speed of light enables us to get close by allowing us to look back in time. When looking out into space, we just need to wait for the light from distant places to reach us. and it shows how things were when the light began its journey. Powerful instruments like Hubble have made it possible to look farther out and farther back than ever before. What cosmologists are seeing is simply astounding.
In the 1920s, astronomer Edwin Hubble discovered that most galaxies appear to be moving away from us at a rate proportional to their distance. The further away a galaxy is, the faster it appears to be moving away from us. This is due to the expansion of the universe.
That expansion began in a titanic explosion called the Big Bang many billions of years ago. The rate of expansion holds the key to estimating the age and size of the universe. This rate is called the Hubble constant. The age and size of the universe can be estimated by running the expansion backwards, until everything is compressed into that infinitely small point of energy from which the universe was generated. The top-ranked scientific justification for building Hubble was to determine the size and age of the universe. The quest to determine the Hubble constant precisely was headed by the Key Project team, a group of astronomers who used Hubble to look for remote, accurate milepost markers, a special class of stars called Cepheid variables. Cepheids have very stable and predictable brightness variations. The period of these variations depends strictly on the physical properties of the star, which can be used to determine their distance very effectively. For this reason, these stars are better known as standard candles. The Cepheids have been used as reliable stepping stones to make distance measurements for supernovae, which are much brighter than Cepheids and so can be seen at far greater distances.
Hubble has measured the light from supernova explosions more accurately than any other instrument, mostly due to its high resolution. From the ground, the image of a supernova generally blends in with the image of its host galaxy. Hubble can clearly distinguish the light from the two sources. Cepheids and supernovae have given a measure of the scale of the universe. Today we know the age of the universe to much higher precision than ever before, around 14 billion years. For many years, astronomers have discussed whether the expansion of the universe would stop in some distant future, making the universe collapse in a fiery big crunch, or whether it would continue to expand ever more slowly. Combined observations of distant supernovae with Hubble and most of the world's top-class telescopes were used to measure distances to remote supernovae. And it looks like the expansion of our universe is nowhere near slowing down. Instead, it seems to be speeding up.
When Hubble was used to measure how the expansion of the universe has changed with time, it turned out quite surprisingly that during the first half of cosmic history, the expansion rate was actually slowing down. Then, a mysterious force, a sort of anti-gravity, made the universe hit the gas pedal, starting the acceleration we see today. This suggests an extraordinary fate for the universe, because it implies that the anti-gravity force is getting stronger all the time. If this continues, it will eventually overwhelm all gravity and catapult the universe into a super-fast acceleration that will shred everything into its constituent atoms. Cosmologists have called this nightmare scenario the Big Rip. we are collecting unexpected news from deep space. Just as geologists dig deeper underground to find ever more ancient fossils, bearing witness to ever more remote epochs, so astronomers excavate deeper and deeper towards the beginning of time by looking for light coming from fainter and thus more distant objects. Hubble started a new era we could call astroarchaeology, and it began during Christmas, 1995. Pointing the world's most sophisticated telescope at the same piece of sky for 10 days in a row may sound a bit strange. And this was what many astronomers thought when they tried it for the first time at the end of 1995.
Deep field observations are long-lasting exposures pointing at a particular region of the sky. They aim to reveal faint objects by collecting as much light as possible over a long period of time. The deeper an observation goes, the fainter are the objects that become visible. Objects in the sky can appear faint either because their intrinsic brightness is low or because their distance is great.
When this experiment was first proposed, an experiment consisting of staring at the same patch of the sky for weeks, nobody really knew whether it would have led to interesting scientific results. But when we first saw the images, the result was astonishing. We could see more than 3,000 galaxies in this small field.
The observed region of sky in Ursa Major, the Big Dipper, was carefully selected to be as empty as possible, so that Hubble would look far beyond the stars of our own Milky Way and out past nearby galaxies. The thousands of galaxies observed in the first deep field were at various stages of evolution and were strung out along a corridor of billions of light years. This allowed astronomers to study the evolution of these objects through time, glimpsing different galaxies at different stages of their lives. After the first deep field, another long exposure was taken in the southern sky. Together, the Hubble Deep Field North and South gave astronomers peepholes to the ancient universe for the first time. Some of the objects viewed on the images were so dim that seeing them would be as difficult as discerning a flashlight on the moon from Earth.
And we could definitely tell that the Hubble Deep Field has opened a new era in observational cosmology, transforming our view of the distant universe.
The Hubble Deep Fields have caused a real revolution in modern astronomy. After the first deep field, almost all ground and space-based telescopes were pointed at the same area for long periods. Some of the most interesting results in astronomy have emerged from this fruitful synergy between instruments of different sizes, in different environments, and with sensitivity to different wavelengths. They gave us the first clear picture of the star formation history throughout the universe. Astonishingly, they showed that star formation peaked within the first few billion years of the universe's creation. At that time, stars were forming at over 10 times the rate they are today.
Once they had begun to discover the most distant universe ever seen, Hubble astronomers tried to push their observations even farther back in time. In 2003 and 2004, Hubble performed its deepest exposure ever, the Hubble Ultra Deep Field. It is a 28-day-long exposure, going much deeper than the earlier Hubble Deep Fields North and South.
The Hubble Ultra Deep Field reveals the first galaxies to emerge from the so-called Dark Ages, the time shortly after the Big Bang when the first stars reheated the cold, dark universe.
Just after the Big Bang, in the newborn, fast-expanding universe, before the era of the stars and galaxies, the distribution of matter was fairly smooth. As time went on, the king of all forces, gravity, started acting. Slowly, but steadily. Under the influence of gravity from the mysterious dark matter, small clumps of normal matter started to coalesce in regions where the density was slightly higher than average. With no stars to light up space, the universe was in its dark age. Where the density of the clumps became higher, even more matter was attracted, and a competition between the expansion of space and gravity took place. Where gravity won, regions stopped expanding and started to collapse in on themselves. The first stars and galaxies were born. Where the matter density was highest, at the intersections between the large web-like structures of matter, the largest structures we know were formed, clusters of galaxies. The deep field images are studded with a wide range of galaxies of various sizes, shapes, and colors. Astronomers will spend years studying the myriad shapes of the galaxies in this image to understand how they formed and have evolved since the Big Bang. In vibrant contrast to the image's rich harvest of classic spiral and elliptical galaxies, there is also a zoo of oddball galaxies littering the field. Some look like toothpicks, others like links on a bracelet. A few appear to be interacting with each other. Their strange shapes are a far cry from the majestic spiral and elliptical galaxies we see today. These oddball galaxies chronicle a period when the universe was more chaotic, when order and structure were just beginning to emerge.
One of the great things about Hubble is that there are many instruments on board that can make different observations at the same time. The Hubble Ultra Deep Field is actually two separate images taken by two instruments, Hubble's ACS camera and the NICMOS instrument. NICMOS sees even further than the ACS. It detects infrared light, and so it's able to reveal the furthest galaxies ever seen because the expanding universe has stretched and weakened the light from these objects so much that they're now only visible at infrared wavelengths.
The Hubble Ultra Deep Field is likely to remain the deepest image of the universe for the next decade or so, until an ESA Ariane rocket launches the James Webb Space Telescope in 2011. Up until today, during the first 15 years of its life, Hubble has orbited the Earth 80,000 times. This is the same as 3.5 billion kilometers, or 24 times the distance from the Earth to the Sun. Hubble has taken more than 500,000 exposures of the universe and created a visual heritage that has shaped the way humanity looks at the universe today. But Hubble's perhaps greatest legacy has been to open our eyes to the incredible beauty of nature, not only out there in the depths of cosmos, but also everywhere around us in our daily lives. And it's nowhere finished yet.